Hello there, and welcome to Cosmic Calm, where we drift through the wonders of space to find the most soothing truths the universe has to offer. Tonight, we're turning our eyes upward to our closest celestial companion, the moon, and discovering the gentle mysteries that have watched over humanity for millions of years. As you settle in for the evening, perhaps feeling the weight of the day begin to lift from your shoulders, we'll explore the quiet majesty of Earth's only natural satellite. These aren't the dramatic facts about lunar missions or scientific breakthroughs. Instead, we're gathering the softest, most peaceful truths about the moon, the kind that can ease your mind and carry you gently toward sleep. The moon has been humanity's nightlight for as long as we've existed, casting its silver glow across our dreams and providing a constant, reassuring presence in the darkness. Tonight we'll discover why this ancient companion feels so comforting, how it moves through space in the most elegant dance imaginable, and the surprising ways it connects to the rhythm of life on Earth. If you find these celestial bedtime stories as soothing as I do, feel free to like this video and subscribe to join our community of peaceful stargazers. You can also share your own favorite moon memories in the comments below. But for now, let your breathing slow, your muscles relax, and allow these gentle lunar facts to wash over you like moonbeams streaming through a bedroom window. The moon is moving away from Earth at the pace of a growing fingernail. Each year, our lunar companion drifts approximately 3 8/10 centimeters farther from our planet. This incredibly slow retreat has been happening for billions of years, and it will continue for billions more. The movement is so gradual that in a human lifetime, the change is completely imperceptible. This gentle separation occurs because of the same force that creates ocean tides. As the moon pulls on Earth's waters, creating the rhythmic rise and fall we see along coastlines, Earth pulls back on the moon in return. But the timing of these gravitational interactions creates a subtle imbalance that gradually pushes the moon into a slightly higher orbit. 4.5 billion years ago, when the moon first formed, it hung much closer to Earth, appearing enormous in the sky. Days were much shorter then, lasting only about 6 hours, because the moon's stronger gravitational pull spun our planet much faster. As the moon has slowly retreated, Earth's rotation has gradually slowed, giving us the comfortable 24-hour days we know today. The process is so perfectly balanced and predictable that scientists can calculate exactly where the moon was thousands of years ago and where it will be thousands of years in the future. There's something deeply comforting about this celestial clockwork, this gentle unwinding of cosmic forces that has been proceeding at the same steady pace since before life existed on Earth. The moon always shows us the same face, like a loyal friend who never turns away. This phenomenon, called synchronous rotation, means that the moon's rotation period exactly matches its orbital period around Earth. It takes approximately 27 days for the moon to complete one rotation on its axis, and exactly the same amount of time to complete one orbit around our planet. This perfect synchronization wasn't always the case. When the moon was young, it spun much faster, showing different faces to Earth as it rotated. But over millions of years, Earth's gravitational pull gradually slowed the moon's rotation until it became locked in this gentle embrace. The same side of the moon has been facing Earth for so long that we've named it the near side, while the hemisphere we never see became known as the far side. This tidal locking is actually quite common throughout the solar system, Many moons of the outer planets show the same faithful behavior, always keeping one face turned toward their parent world. It's as if these celestial bodies have chosen to maintain an eternal gaze, a cosmic devotion that spans billions of years. The familiar features we see on the moon's surface, the dark areas called Maria and the bright highlands, have remained in the same positions throughout all of human history. Every civilization that has ever looked up at the night sky has seen exactly the same lunar face that greets us today. This consistency provides a sense of permanence and stability that feels deeply reassuring in our ever-changing world. The moon's surface is covered in a soft powder called regolith that sparkles like fine dust. This lunar soil wasn't created by wind or water erosion like the dirt beneath our feet on Earth. Instead, it formed over billions of years as meteorites and cosmic particles gently bombarded the moon's surface, gradually grinding solid rock into increasingly fine particles. The regolith varies in depth across the moon's surface, ranging from a few meters in some areas to over 20 meters in others. In the ancient lunar highlands, this cosmic dust has been accumulating for nearly 4 billion years, creating deep blankets of powder so fine it feels almost like flour. The particles are incredibly small, much finer than beach sand, and they stick together in a way that would feel strange to human hands. When the Apollo astronauts walked on the moon, they described the regolith as having an unusual texture. It compressed under their boots like wet sand, but when disturbed, it flowed like dry powder. The dust clung to their spacesuits and equipment with an almost magnetic attraction, creating challenges they hadn't anticipated, but also leaving beautiful footprints that will remain pristine for millions of years. Without wind or rain to disturb them, every footprint left by human visitors remains exactly as it was made over 50 years ago. The tire tracks from the lunar rovers still curve across the surface in perfect detail. This preservation of human presence creates a touching connection between Earth and its companion, a permanent record of the few brief moments when humans walked on another world. The moon experiences the most gentle sunrises and sunsets imaginable, lasting for hours instead of minutes. Because the moon rotates so slowly, taking nearly 28 Earth days to complete one turn, the transition from day to night unfolds with extraordinary patience. The sun appears to creep across the lunar sky at a pace so leisurely it would be difficult to perceive its movement with the naked eye. During a lunar sunrise, shadows retreat across the surface with dreamlike slowness, revealing craters and mountains in gradually changing light. The boundary between day and night, called the terminator, moves across the moon's face at only about 15 kilometers per hour. This gentle progression means that any particular spot on the moon experiences roughly 14 Earth days of continuous sunlight, followed by 14 days of unbroken darkness. The temperature changes just as gradually as the light. As the sun slowly rises over a lunar landscape, the surface warms from the bitter cold of space to surprisingly comfortable temperatures. In some areas near the lunar equator, the surface temperature during the day reaches about 20 degrees Celsius, roughly room temperature on a mild spring day. This slow thermal cycle creates a rhythm unlike anything on Earth, where sunrise and sunset mark the hurried pace of our 24-hour days. The moon's measured approach to day and night feels almost meditative, a cosmic breathing that expands and contracts over weeks rather than hours. It's a reminder that time itself can move at different paces depending on where you stand in the universe. the moon's gravity is exactly 1/6 as strong as Earth's, creating a world where everything moves with ethereal grace. A person who weighs 70 kilograms on Earth would weigh only about 12 kilograms on the moon. This gentle gravitational pull means that movements that require effort and strength on Earth become fluid and effortless on the lunar surface. The Apollo astronauts discovered that walking normally was almost impossible in this reduced gravity. Instead, they developed a peculiar hopping gait that became iconic in the footage of their lunar explorations. They could leap surprisingly high with minimal effort, and their movements had a dreamlike quality, as if they were moving through water or floating through space. A basketball thrown on the moon would arc through the sky in a perfect parabola, traveling 6 times farther than the same throw would carry on Earth. Objects fall much more slowly, giving you plenty of time to catch something you've dropped. Even dust kicked up by footsteps seems to hang in the airless sky longer than it should, creating graceful arcs that follow mathematical curves with perfect precision. This gentle gravity would make many earthly activities feel magical. Dancing would become a form of slow-motion flight. Simple jumps would carry you several meters into the air. The weight of fatigue would lift from your shoulders, and every movement would feel supported by invisible hands, guiding you through this low-gravity wonderland. The moon has no atmosphere to scatter sunlight, creating the deepest, most perfect black sky imaginable. During the lunar day, when the sun shines brightly on the surface, the sky remains utterly dark, filled with stars that shine with crystal clarity. This creates one of the most beautiful contrasts in the solar system. Brilliant sunlight illuminating a stark landscape beneath a sky darker than the darkest night on Earth. Without an atmosphere to create weather, the moon knows no clouds, no rain, no wind. The silence is absolute, broken only by the occasional vibrations transmitted through the solid ground. Radio communications and the sounds of equipment carried through spacesuits were the only audio experiences the Apollo astronauts had on the lunar surface. Otherwise, the moon exists in perfect, eternal quiet. This absence of atmosphere also means there's no blue sky, no golden sunsets, no scattered light of any kind. Shadows are sharp and absolute, creating stark contrasts between areas of brilliant illumination and regions of complete darkness. The lighting has a quality unlike anywhere on Earth, harsh yet beautiful, alien yet somehow peaceful in its consistency. Stars that are invisible from Earth due to atmospheric interference shine brilliantly from the moon's surface. The Milky Way stretches across the lunar sky with stunning clarity, and distant galaxies become visible to the naked eye. It's as if the moon serves as a natural observatory, providing the clearest possible view of the cosmos beyond our solar system. The moon's craters tell stories that span billions of years, each one a gentle record of cosmic history preserved in stone. Unlike Earth, where weather and geological activity constantly reshape the surface, the moon's craters remain exactly as they were formed, creating a museum of ancient impacts that stretches back to the very beginning of our solar system. The largest craters, visible even to the naked eye as dark patches on the moon's surface, were created by massive asteroids that struck billions of years ago. These ancient scars have softened over time, not through erosion, but through the gentle accumulation of cosmic dust and the occasional smaller impact that gradually rounds their sharp edges. The result is a landscape of rolling hills and shallow depressions that speaks of unimaginable age and patient endurance. Some of the moon's most beautiful features are the rays that extend outward from certain craters like delicate fingers of light. These bright streaks, best seen during a full moon, are made of material that was thrown out during relatively recent impacts. The rays from Tycho crater stretch for over 1,500 kilometers across the lunar surface, creating patterns that look almost like artwork painted on a cosmic canvas. Each crater has its own personality and story. Some are perfectly circular, others are elongated from impact's angles. Some have central that struck at shallow peaks that rose up moments after impact, like drops of water frozen in time. Others are surrounded by terraced walls that formed as the crater's edges collapsed inward in slow motion. Walking among these formations would feel like exploring a vast sculpture garden created by forces beyond human comprehension. The moon wobbles gently as it orbits Earth like a slow dance partner keeping time to cosmic music. This subtle motion, called libration, allows us to see slightly more than half of the moon's surface over time. The wobble is so gentle that it takes careful observation to notice, but it means that about 59% of the moon's surface is visible from Earth at different times. This lunar wobble happens for several reasons, all of them perfectly natural and predictable. Sometimes the moon moves a little faster in its orbit, sometimes a little slower because its path around Earth is slightly elliptical rather than perfectly circular. The moon also nods up and down slightly because its axis is tilted just a few degrees compared to its orbital plane. These small movements create a soothing rhythm that has been going on for billions of years. The moon rocks back and forth by about 7 degrees, tips up and down by about 6 degrees, and these motions combine to create a gentle swaying that reveals hidden valleys and crater rims along the lunar horizon. It's as if the moon is slowly turning its head from side to side, offering us glimpses of regions that would otherwise remain forever hidden. Ancient astronomers noticed this subtle dance and gave it the name libration, from the Latin word meaning to balance or oscillate. They found comfort in tracking these small movements, recognizing them as part of the moon's natural behavior rather than random variations. The predictability of libration became one of many ways that lunar observations helped early scientists understand that celestial motions follow orderly mathematical patterns. The moon influences Earth's rotation in the most subtle and stabilizing way imaginable. Our planet spins on its axis like a top, but instead of wobbling wildly as it slows down, Earth maintains a remarkably steady orientation thanks to the moon's gravitational presence. Without this lunar bowl chaotically through space causing influence, our planet would tum dramatic climate shifts that would make life as we know it impossible. The moon acts like a gyroscopic stabilizer, keeping Earth's axial tilt steady at about 23.5 degrees. This consistent tilt gives us our regular seasons with their predictable patterns of warmth and cold, growth and dormancy. The stability is so reliable that we can calculate the exact time of sunrise and sunset thousands of years into the future, knowing that the moon will continue its faithful gravitational guidance. This stabilizing influence extends to Earth's climate in ways that create the perfect conditions for life. Without the moon, our planet's tilt could vary wildly from 0 degrees to more than 85 degrees over periods of millions of years. Such dramatic changes would cause ice ages to come and go unpredictably, and the tropics might sometimes freeze while the polar regions baked in constant sunlight. The moon's steadying presence means that Earth's climate has remained stable enough for life to evolve and flourish over billions of years. Ocean currents flow in predictable patterns, weather systems follow seasonal rhythms, and living creatures can adapt to environmental changes that occur gradually rather than catastrophically. In this way, the moon serves as Earth's faithful guardian, maintaining the gentle stability that makes our world a haven for life. The lunar Maria, those dark patches that form the face we see in the moon, are actually ancient lava flows that cooled billions of years ago. These smooth, dark plains were once oceans of molten rock that bubbled up from the moon's interior during a period of intense volcanic activity. The lava flowed gently across the lunar surface, filling in the largest impact craters and creating the relatively flat areas we see today. The word Maria is Latin for seas because early astronomers thought these dark regions might actually be bodies of water. While we now know they're made of solid basaltic rock, the name stuck, and it carries a poetic truth about their appearance. From Earth, the Maria do look like calm, dark waters reflecting starlight, creating patterns that have inspired countless stories and legends throughout human history. These ancient lava flows tell a story of a more active moon, one that was still warm enough inside to generate volcanic eruptions. The largest of these flows, called Mare Imbrium, or the Sea of Rains, covers an area larger than Alaska. The lava that formed it flowed so gently that it preserved many of the smaller craters it encountered, creating islands of highland material that rise like archipelagos from the dark volcanic plains. The Maria formed during a relatively brief period in lunar history, mostly between 3 and 4 billion years ago. Since then, the moon has been volcanically quiet, its interior too cool to generate new lava flows. This means that the patterns we see in the lunar Maria are snapshots of ancient activity, preserved perfectly in the airless environment like photographs taken billions of years ago and never faded by time. The moon's interior contains a small, partially molten core that still glows with heat from its formation. Deep beneath the familiar surface features lies a core about 700 kilometers in diameter, roughly the size of the dwarf planet Pluto. This metallic heart of the moon remains warm after 4.5 billion years, slowly cooling at a rate so gradual it will take billions more years to solidify completely. Surrounding the core is a thick mantle of rock that makes up most of the moon's interior volume. This rocky layer experienced the volcanic activity that created the Maria, and it still retains enough heat to remain slightly flexible. Seismometers left by Apollo astronauts detected moonquakes that originate deep in this mantle. Gentle tremors that show the lunar interior is still slowly adjusting as it cools. The outermost layer is the crust, a shell of lighter rock that averages about 70 kilometers thick on the side facing Earth, and nearly twice that thickness on the far side. This asymmetry gives the moon a slightly lopsided structure, with its center of mass offset toward Earth. The thicker far side crust explains why we see so few Maria there. The crust was simply too thick for ancient lava flows to break through to the surface. Even today, instruments can detect the faint magnetic field generated by the moon's core. While much weaker than Earth's magnetic field, this subtle magnetism provides evidence that the lunar interior remains dynamic. Rocks brought back by Apollo missions show that the moon once had a much stronger magnetic field, suggesting its core was more active in the past. The gradual weakening of this field over billions of years tells a story of slow, patient cooling that continues today. The moon creates the most peaceful tides imaginable, gently lifting and lowering Earth's oceans in a rhythm that has remained constant for millions of years. These tidal cycles happen twice each day as the moon's gravity pulls on the water closest to it, creating a bulge that follows the moon's position in the sky. On the opposite side of Earth, another tidal bulge forms as the planet itself is pulled slightly toward the moon, leaving the water behind. The result is a gentle rise and fall of sea level that varies by location, but follows the same basic pattern everywhere on Earth. In the open ocean, tidal changes are usually only about 1 meter, creating a slow, breathing motion that marine life has adapted to over countless generations. Along certain coastlines, the shape of the seafloor and shoreline can amplify these tides, but even the most dramatic tidal ranges unfold gradually over hours. This tidal rhythm creates one of Earth's most reliable natural clocks. Coastal creatures time their activities to the ebb and flow of the tides, and humans have used tidal patterns for navigation and fishing for thousands of years. The predictability is so precise that tide tables can be calculated years in advance, showing exactly when high and low tides will occur at any location on Earth. The tides also create a subtle but important mixing of ocean waters, helping to distribute heat, nutrients, and oxygen throughout the seas. This gentle stirring contributes to ocean currents that regulate Earth's climate and support marine ecosystems. In tidal pools along rocky shores, the twice-daily rise and fall of water creates miniature worlds, where life adapts to the rhythm of exposure and submersion, all choreographed by the moon's faithful gravitational pull. The moon's phases unfold like a cosmic breathing exercise, expanding from darkness into light and back again with perfect regularity. Each lunar month begins with the new moon when our celestial companion appears completely. But this darkness isn't and the pause, like it absence, is a beginning between breaths that makes the next inhale possible. As the moon continues its orbital dark from Earth's perspective, Journey, a slender crescent, appears in the western sky just after sunset. This delicate curve of light grows wider each night, waxing toward the first quarter when exactly half the lunar disk glows with reflected sunlight. The progression is so gradual that the change barely perceptible, yet over from one night to the next is the course of a week. The transformation is unmistakable. The full moon arrives like a gentle climax to this celestial symphony, flooding the night landscape with silver radiance that has inspired poets and dreamers throughout history. For 3 nights around the full moon, the difference in illumination is so subtle that the moon appears completely round, giving us several evenings to appreciate its full glory before it begins the graceful retreat toward darkness. The waning phases mirror the waxing ones in reverse, creating a perfectly symmetrical cycle that has remained unchanged since before life began on Earth. Ancient cultures tracked these phases to mark the passage of time, plant crops, and plan ceremonies. The lunar calendar they created reflects humanity's deep connection to this celestial rhythm that continues to influence our lives in ways both obvious and subtle. The moon's surface temperature changes create the most extreme climate imaginable, yet it happens so slowly that it feels almost meditative. During the 14 Earth days of lunar daylight, surface temperatures gradually rise from the bitter cold of space to surprisingly warm conditions. In some areas, the temperature reaches about 120 degrees Celsius, hot enough to boil water, while in shadowed regions it remains perpetually frozen. But this isn't the violent, chaotic temperature swing you might expect. The change happens so gradually over 2 weeks that it's like watching a very slow sunrise that lasts for days. The thermal transition occurs at a pace of only a few degrees per hour, giving the lunar landscape time to adjust gently to each temperature change. The most fascinating aspect of lunar temperature is how quickly it drops once the sun sets. Without an atmosphere to trap heat, the surface begins cooling immediately, and within hours of sunset, temperatures plummet to minus 170 degrees Celsius. This rapid cooling creates a sharp contrast with the gradual warming that preceded it, like a patient exhale following a long, slow inhale. Some regions of the moon never experience these temperature extremes at all. Deep inside certain polar craters, areas exist that have remained in permanent shadow for billions of years. These regions are among the coldest places in the solar system, even colder than the surface of Pluto. Yet their eternal darkness provides a kind of stability, a constant condition that never changes regardless of the sun's position. The moon's weak magnetic field creates invisible streams of charged particles that flow gently around our satellite like cosmic rivers. Unlike Earth's strong magnetic field that deflects most solar wind, the moon's magnetic environment is subtle and complex, creating pockets of magnetism scattered across its surface like islands in a vast ocean. These magnetic anomalies formed billions of years ago when the moon's core was more active and generated a stronger global magnetic field. As the lunar interior cooled and this field weakened, only scattered remnants remained, preserved in certain types of rock like frozen memories of the moon's more magnetic past. Today, these areas create gentle deflections in the solar wind. The stream of particles flowing constantly from the sun. Spacecraft orbiting the moon can detect these magnetic streams as they flow around and through the lunar environment. The interactions create beautiful, invisible sculptures of magnetic force that change and shift as the moon passes through different regions of Earth's own magnetic field. Sometimes the moon travels through Earth's magnetotail, the elongated portion of our planet's magnetic field that stretches away from the sun, creating even more complex magnetic interactions. This weak magnetism also affects the very fine dust on the lunar surface. In some regions, magnetic forces cause dust particles to levitate slightly above the ground, creating thin clouds of electrostatically charged particles that hover just above the surface. These dust clouds are so tenuous they're barely detectable, but they add another layer of subtle beauty to the moon's already enchanting environment. The far side of the moon remains one of the most pristine environments in the solar system, completely shielded from Earth's radio signals and electronic noise. This hemisphere, sometimes mistakenly called the dark side, actually receives just as much sunlight as the near side, but it offers something even more valuable than darkness. It provides perfect radio silence. The moon's bulk blocks all electromagnetic radiation from Earth, creating a zone of radio quiet that astronomers dream of using for sensitive observations. No cell phone signals, no television broadcasts, no radar pulses can reach the far side. It's the quietest place in the inner solar system for radio astronomy, offering a window to the universe uncontaminated by human technology. The landscape of the far side differs dramatically from the familiar face we see from Earth. Instead of the smooth, dark maria that dominate the near side, the far side is heavily cratered and mountainous, covered with bright highland material that reflects sunlight brilliantly. The South Pole Aitken Basin, one of the largest impact craters in the solar system, dominates the far side's southern hemisphere like a vast, ancient scar. This hidden hemisphere remained completely unknown until spacecraft began orbiting the moon in the late 1950s. The first images of the far side revealed an alien landscape that looked nothing like the moon we thought we knew. Today, detailed maps show every crater and mountain on the far side, but it still feels mysterious and remote, a world that no human eye has ever seen directly except through the windows of spacecraft. The moon's gravity creates subtle variations across its surface that tell stories about its interior structure. These gravitational anomalies, called mascons, occur where dense material lies beneath the surface, usually associated with the large impact basins filled with heavy volcanic rock. The gravitational pull in these areas is slightly stronger than average, creating invisible hills and valleys in the moon's gravitational field. Spacecraft orbiting the moon must constantly adjust their paths to compensate for these gravitational irregularities. What appears to be a perfectly smooth orbital path from Earth becomes a complex dance of tiny course corrections as the spacecraft encounters stronger and weaker gravitational pulls. These variations are so subtle that they're measured in fractions of a millimeter per second, but they're consistent and predictable. The mascons formed when massive asteroids struck the moon billions of years ago, excavating enormous craters that were later filled with dense volcanic lava. The weight of this extra material compressed the lunar crust beneath it, creating permanent indentations in the moon's gravitational field. Today, these gravitational signatures provide clues about the moon's internal structure and the violent impacts that shaped its surface. Scientists use these gravitational maps to peer inside the moon without drilling or digging. By measuring tiny changes in spacecraft orbits, they can detect dense rock formations, empty lava tubes, and even variations in crustal thickness. It's like using gravity as a gentle probe that reveals the moon's hidden architecture through the subtle influence it exerts on passing objects. The moon experiences seismic activity that creates the gentlest earthquakes imaginable, called moonquakes. These lunar tremors are much weaker than Earth's earthquakes, but they last much longer, sometimes continuing for hours after they begin. The moon's dry, rigid structure allows seismic waves to propagate much farther than they would through Earth's more flexible, water-saturated rocks. Apollo astronauts installed seismometers on the lunar surface that detected thousands of moonquakes over nearly a decade of operation. Most of these were incredibly subtle, registering magnitudes that would be barely detectable on Earth. The strongest moonquakes measured only about magnitude 5 on the Richter scale, strong enough to feel, but not strong enough to cause damage to structures. The moonquakes fall into several categories, each with its own gentle characteristics. Deep moonquakes occur about 700 kilometers below the surface, probably caused by tidal stresses as Earth's gravity flexes the moon's interior. Shallow moonquakes happen closer to the surface and may be related to the gradual cooling and contraction of lunar rocks. Thermal moonquakes occur when the lunar surface heats up during sunrise after the long, cold lunar night. As rocks expand in the warming sunlight, they create tiny fractures and adjustments that register as seismic events. These thermal quakes follow the terminator as it moves across the moon's surface, creating a wave of gentle seismic activity that circles the moon every lunar day. The moon's ancient impact craters serve as natural amphitheaters that would create the most unusual acoustic effects. Although sound cannot travel through the moon's airless environment, if you could somehow create an atmosphere inside one of these circular formations, the acoustic properties would be extraordinary. The curved walls would focus and reflect sound waves in ways that don't exist anywhere on Earth. Large craters like Copernicus or Tycho have nearly perfect circular symmetries that would act like enormous parabolic reflectors. A whisper spoken at the center of such a crater, if there were air to carry it, would be focused and amplified by the curved walls, potentially creating the most perfect natural echo chambers in the solar system. The terraced walls of many large craters would create multiple reflections at different delays, building complex reverberations that would layer sound upon sound in intricate patterns. Some craters have central peaks that would act as acoustic focal points, creating unique sound effects that have no earthly equivalent. Even without an atmosphere, these crater formations demonstrate the moon's perfect preservation of ancient geometries. Impact craters on Earth are quickly modified by erosion, but lunar craters maintain their original acoustic properties unchanged for billions of years. They stand as silent concert halls waiting for an audience that may never come. Their perfect acoustics preserved in the vacuum of space. The lunar surface contains tiny glass beads created by ancient impacts, scattered across the regolith like microscopic jewels. When meteorites strike the lunar surface at incredible speeds, they generate temperatures hot enough to melt rock instantly. This molten material gets thrown into the airless sky where it cools and solidifies into perfectly spherical glass droplets before falling back to the surface. These impact glasses come in many colors, from clear and amber to deep green and brown, depending on the chemical composition of the rock that was melted. Some are so small they can only be seen under a microscope, while others are large enough to pick up by hand. Each one is a tiny time capsule, preserving the exact moment of an impact that happened millions or billions of years ago. The glass beads are scattered throughout the lunar soil, mixed with fragments of shattered rock and cosmic dust. Apollo astronauts collected thousands of these microscopic spheres without even realizing it, bringing them back to Earth, where scientists discovered their remarkable properties. Under magnification, they reveal perfect spherical shapes that could only form in the absence of gravity and atmosphere. Some of the glass beads contain tiny bubbles of gas that were trapped during their formation. These bubbles preserve samples of the ancient lunar atmosphere, if it existed, or gases released from the impacting meteorite. Studying these microscopic time capsules helps scientists understand the history of impacts on the moon and the conditions that existed during different periods of lunar evolution. The moon's orbit traces a gentle ellipse around Earth that changes slowly over time, creating subtle variations in our satellite's apparent size and brightness. At its closest approach, called perigee, the moon appears about 14% larger and 30% brighter than when it's at its farthest point, called apogee. This variation happens gradually over the course of each month, so subtle that most people never notice the difference. The elliptical orbit also affects the moon's speed as it travels around Earth. When closer to our planet, the moon moves slightly faster, completing its orbit in a shorter time. When farther away, it slows down, taking longer to complete its circuit. This variation in orbital speed is one of the factors that creates the gentle libration we discussed earlier, the slight wobbling motion that allows us to see a bit more than half of the moon's surface over time. The shape and orientation of the moon's orbit change slowly over much longer periods, following complex cycles that repeat over thousands of years. Sometimes the orbit is more circular, sometimes more elliptical. Sometimes the closest approach brings the moon nearer to Earth, sometimes farther away. These long-term changes create subtle variations in tides and climate that unfold over geological timescales. Ancient astronomers tracked these orbital variations with remarkable precision, using them to predict eclipses and understand the mechanics of celestial motion. The predictability of these changes, even over thousands of years, demonstrates the stable, mathematical nature of gravitational interactions. The moon's orbit is not random or chaotic, but follows precise laws that allow us to calculate its position millions of years into the past or future. The moon's rotation and revolution are perfectly synchronized in a cosmic dance that have been choreographed by gravity over billions of years. This celestial waltz means that the same lunar hemisphere has been facing Earth since long before the first stirrings of life in our planet's ancient oceans. The gravitational forces that created this synchronization worked gradually, like a patient teacher guiding a student through the steps of an intricate dance until the movements became natural and effortless. This tidal locking process happens slowly and gently, with Earth's gravitational pull acting like invisible hands that gradually slowed the moon's rotation until it matched its orbital period exactly. The energy from the moon's original faster rotation wasn't lost, but was converted into orbital energy, which is why the moon has been slowly spiraling away from Earth ever since. It's a perfect example of how the universe conserves energy while creating beautiful, stable patterns. The synchronization is so precise that the moon's rotation and revolution match to within tiny fractions of a degree. This isn't approximate or close, it's exact, maintained by the same gravitational forces that keep the system stable. If you could stand on the lunar surface, Earth would appear to hang motionless in the sky, neither rising nor setting, but maintaining the same position throughout the entire lunar day and night cycle. This locked rotation creates unique perspectives across the lunar surface. From some locations, Earth appears directly overhead, a blue marble suspended in the black sky. From other areas, Earth hovers near the horizon, partially hidden behind lunar mountains. And from the far side, Earth never appears at all, leaving those regions with an unobstructed view of deep space that remains constant throughout the moon's orbit. The lunar highlands rise like gentle mountains across vast regions of the moon's surface, created by the same impacts that form the large craters but expressed in a completely different way. These elevated regions represent the moon's original crust, pushed upward and outward by the tremendous forces of ancient collisions. Unlike Earth's mountains, which form through tectonic activity and volcanic processes, lunar highlands are essentially frozen splash patterns from impacts that happened billions of years ago. The highlands appear bright white from Earth because they're composed of light-colored rock called anorthosite, rich in the mineral feldspar. This ancient rock formed when the moon's surface was covered by a global ocean of molten rock called a magma ocean. As this primordial sea cooled, lighter minerals floated to the surface like cream rising to the top of milk, creating the foundation for the highlands we see today. These elevated regions tell the story of the moon's violent early history, when massive asteroids bombarded the lunar surface during a period called the Late Heavy Bombardment. Each impact not only created craters, but also threw enormous amounts of material across the surface, building up the highland regions grain by grain. The process was chaotic yet gradual, like a very slow cosmic snowfall that accumulated over millions of years. Walking through the lunar highlands would feel like exploring an ancient, weathered landscape where every hill and valley has remained unchanged for billions of years. The gentle slopes and rounded peaks speak of unimaginable age, their sharp edges softened by eons of micrometeorite impacts and the gradual accumulation of cosmic dust. These are some of the oldest surfaces in the solar system, preserving conditions from when the planets were still young. The moon's weak atmosphere, called an exosphere, is so thin it's barely more substantial than the vacuum of space itself. This gossamer envelope consists of individual atoms and molecules that are so spread out they rarely collide with each other. The entire atmospheric mass of the moon weighs less than 10 tons, compared to Earth's atmosphere, which weighs over 5 quintillion tons. This tenuous atmosphere comes from several gentle sources. Solar wind particles strike the lunar surface and knock atoms of sodium, potassium, and other elements into space where they briefly orbit the moon before either escaping entirely or falling back to the surface. Radioactive decay of elements in lunar rocks also releases atoms into the exosphere, while occasional impacts by meteorites vaporize small amounts of surface material. The lunar atmosphere changes constantly as atoms are added and lost in a delicate balance. During the lunar day, more atoms are knocked free by solar radiation, thickening the exosphere slightly. During the long lunar night, fewer new atoms are added while existing ones gradually drift away into space. The result is an atmospheric density that varies by location and time, sometimes becoming slightly denser, sometimes thinner, but always remaining incredibly sparse. Despite its extreme thinness, this wispy atmosphere creates beautiful effects that can only be seen from space. Sodium atoms in the exosphere glow with a characteristic yellow light when excited by solar radiation, creating a faint aureole around the moon that's visible to sensitive instruments. This ghostly glow extends thousands of kilometers into space, making the moon appear like a dim comet with an invisible tail of glowing gas. The moon's surface features cast shadows that remain sharp and well-defined because there's no atmosphere to scatter light and soften their edges. These shadows create dramatic contrasts between areas of brilliant illumination and regions of absolute darkness. The boundary between light and shadow, called the terminator, moves across the lunar surface like a slow, precise knife edge that reveals topographic details with stunning clarity. Near the terminator, small craters and rocks cast long shadows that make them appear much larger and more dramatic than they actually are. A boulder only a few meters tall can cast a shadow hundreds of meters long when the sun is low on the lunar horizon. These elongated shadows create a constantly changing landscape of light and dark that shifts hour by hour as the terminator moves across the surface. The absence of atmospheric scattering also means that shadows on the moon are illuminated only by light from surrounding reflect surfaces. In areas with bright highland material nearby, shadows receive enough reflected light to reveal details within them. But in regions surrounded by dark maria, shadows become pools of absolute blackness where no details are visible at all. This stark lighting creates a surreal beauty unlike anything on Earth. Landscapes appear almost painted, with areas of pure white illumination adjacent to regions of complete darkness. The contrast is so extreme that cameras have difficulty capturing both bright and shadowed areas in the same image, requiring multiple exposures to reveal the full range of lunar topography. The moon's influence on Earth's oceans extends far beyond the familiar, twice-daily tides to create subtle patterns that affect marine life in ways scientists are still discovering. The gravitational pull doesn't just move water up and down, but also creates horizontal currents that flow back and forth across continental shelves. These tidal currents carry nutrients, distribute marine organisms, and create mixing patterns that influence ocean chemistry on a global scale. The strength of tidal forces varies with the moon's distance from Earth and its position relative to the sun. When the moon is closest to Earth during its elliptical orbit, tidal ranges increase noticeably, creating what are called perigean spring tides. These enhanced tides can be 30% stronger than average, gently but persistently reshaping coastlines and affecting the behavior of countless marine species. Many marine creatures have evolved to synchronize their reproductive cycles with specific tidal conditions created by the moon's gravitational influence. Certain species of fish, crabs, and marine worms spawn only during particular combinations of tidal height and lunar phase, timing their reproduction to take advantage of optimal conditions for their offspring's survival. This biological clock has been running for millions of years, creating an intricate web of life timed to celestial mechanics. The moon's tidal influence even affects groundwater and underground rivers, creating subtle rises and falls in water table levels that follow lunar cycles. Wells and springs sometimes show slight variations in flow rate that correspond to the moon's position, demonstrating that the lunar gravitational effect penetrates deep into Earth's crust. These underground tides are much smaller than ocean tides, but reveal how thoroughly the moon's influence permeates our planet's water systems. The lunar soil contains a record of solar activity stretching back billions of years, preserved in microscopic particles that have been accumulating on the moon's surface since its formation. Unlike Earth, where geological processes constantly materials, the moon's reg-recycle surface, OLITH, acts like a cosmic library, storing information about the sun's behavior across geological timespans. Solar wind particles become embedded in the surfaces of individual dust grains, creating tiny archives of solar composition and intensity. Scientists can extract these particles in laboratory settings and analyze them to understand how the sun's output has changed over time. This information provides crucial insights into stellar evolution and helps predict how the sun might behave in the future. The regolith also contains particles from beyond our solar system, interstellar dust grains that have traveled across the galaxy before settling gently on the lunar surface. These microscopic visitors carry information about the composition of distant stars and the chemistry of interstellar space. Each grain is a tiny messenger from the cosmos, bringing news of conditions in regions so remote that light from them takes years to reach us. Cosmic ray particles, high-energy protons, and atomic nuclei accelerated by distant stellar explosions constantly bombard the lunar surface and become trapped in the crystal structure of lunar minerals. These particles create microscopic damage tracks that scientists can study to understand the intensity of cosmic radiation over millions of years. The moon serves as a passive detector, recording the radiation environment of our cosmic neighborhood with perfect fidelity. The moon's formation created Earth's largest and most constant companion, but it also established a gravitational partnership that has shaped both worlds in profound ways. The impact that created the moon also tilted Earth's axis to its current angle, giving us the seasonal variations that have remained stable throughout Earth's history. Without this axial stability, our planet's climate would be chaotic and unpredictable, making complex life much more difficult to establish and maintain. The debris from the moon forming impact mixed materials from both the early Earth and the impacting object, creating a satellite with a unique composition that reflects both worlds. Chemical analysis of lunar samples shows that the moon contains elements and proportions that tell the story of this ancient collision. Iron from the impactor's core, silicates from both mantles, and lighter elements that were vaporized and recondensed all contribute to the moon's distinctive mineralogy. The gravitational interaction between Earth and the moon has been gradually slowing our planet's rotation since the moon's formation. Early in Earth's history, days were much shorter, perhaps only 6 hours long, and the moon appeared enormous in the sky. As the moon has moved away and Earth's rotation has slowed, both worlds have settled into the comfortable rhythm we know today, with 24-hour days and a moon that appears just the right size to create perfect solar eclipses. This ongoing gravitational dance will continue for billions of years, with the moon slowly receding and Earth's rotation gradually slowing until both are tidally locked to each other. In this distant future, Earth days will be about 47 of our current days long, and the moon will appear stationary in the sky from one hemisphere while remaining forever invisible from the other. It's a fate written in the mathematics of orbital mechanics, as predictable as sunrise. The moon's lack of magnetic field allows solar wind particles to strike its surface directly, creating a constantly changing electrical environment that varies with solar activity. During periods of high solar activity, the lunar surface builds up electrical charges that can affect dust particles and create unusual phenomena. These electrostatic effects are strongest near the terminator, where temperature differences are greatest and electrical gradients build up most readily. Lunar dust particles can become electrically charged and levitate slightly above the surface, especially in areas where sunlight and shadow meet. This creates thin, invisible clouds of floating dust that move and shift with changing electrical conditions. The effect is so subtle it's barely detectable, but it adds another layer of dynamic behavior to what appears to be a completely static environment. The electrical charging also affects spacecraft and equipment on the lunar surface. Solar panels can build up static charges that must be carefully managed to prevent damage to sensitive electronics. Spacesuits worn by astronauts accumulate dust that clings with electrostatic attraction, making it difficult to remove and potentially hazardous if it gets into life support systems. These electrical phenomena create auroras of sorts, though not the colorful displays we see on Earth. When solar wind particles interact with the moon's weak magnetic anomalies, they can create faint glows of excited atoms that are visible only to sensitive instruments. These lunar auroras are much more subtle than their terrestrial counterparts, appearing as gentle brightening in specific wavelengths of light, rather than the dramatic curtains of color that dance across Earth's polar skies. The moon's surface contains water ice hidden in permanently shadowed craters near its poles, creating some of the most pristine and ancient reservoirs of water in the solar system. These deposits have been accumulating for billions of years as comets and water-bearing asteroids struck the lunar surface, with some of the water vapor eventually finding its way to the coldest places on the moon, where it froze and remained stable. The ice deposits exist in regions that have been dark for billions of years, never receiving direct sunlight and maintaining temperatures colder than anywhere on Earth's surface. These permanently shadowed regions act like natural freezers, preserving water molecules that may have arrived on the Moon during the earliest days of the solar system. Some of this ice could contain clues about the composition of the primordial solar nebula from which all planets formed. Recent missions have detected these ice deposits using neutron spectrometers and other instruments that can sense hydrogen atoms even when they're frozen and hidden beneath layers of dust. The ice appears to be mixed with the regolith rather than forming pure deposits, creating a muddy mixture that would require processing to extract clean water. The total amount of water ice stored in these polar regions may be substantial, potentially enough to support future lunar exploration missions. The preservation of these ice deposits demonstrates the Moon's ability to maintain stable conditions over geological timespans. Unlike Earth, where water cycles constantly through the atmosphere and oceans, lunar ice remains exactly where it was deposited, creating a frozen record of water delivery to the inner solar system. These deposits represent some of the most stable and long-lasting features on the Moon's surface, unchanged for billions of years and likely to remain frozen for billions more. The Moon serves as Earth's natural timekeeper, its predictable phases and position providing humanity with one of the most reliable methods of measuring time throughout history. Long before mechanical clocks or atomic timekeepers, people used lunar cycles to track the passage of days, months, and seasons. The word month itself derives from moon, reflecting this fundamental connection between lunar cycles and human timekeeping. The lunar calendar based on the Moon's phases contains about 12 cycles per year, creating a natural subdivision of time that cultures worldwide adopted independently. This lunar year of approximately 354 days doesn't match exactly with Earth's orbital period around the Sun, creating the need for intercalary months and complex calendar adjustments that have occupied mathematicians and astronomers for millennia. The Moon's position against the background stars provided ancient navigators with a celestial compass that helped them cross oceans and traverse continents. By knowing the Moon's location relative to specific star patterns, travelers could determine their approximate position and direction even when landmarks were not visible. This lunar navigation system worked reliably anywhere on Earth and required only careful observation and knowledge of celestial patterns. Modern timekeeping still relies on astronomical observations that include precise measurements of the Moon's position and motion. The Moon's gravitational influence affects Earth's rotation speed slightly, creating variations that must be accounted for in the most precise time measurements. Leap seconds are occasionally added to coordinated universal time to keep our clocks synchronized with Earth's actual rotation, which is influenced by tidal interactions with the Moon. The Moon's relationship with Earth creates one of the most stable partnerships in the solar system, a gravitational bond that has endured through cosmic catastrophes and planetary evolution. This celestial marriage began in violence when a Mars-sized object collided with the early Earth. But from that chaos emerged a harmony that has lasted for 4.5 billion years. The partnership continues to evolve slowly, with both worlds adjusting to each other's gravitational influence in ways that maintain perfect balance. The distance between Earth and the Moon changes gradually over time, but their gravitational connection remains constant and predictable. Even as the Moon slowly retreats, the fundamental relationship stays stable, like a cosmic dance where the partners move farther apart while maintaining the same rhythm. This stability has allowed both worlds to develop and maintain the conditions necessary for Earth's climate systems and the Moon's preserved landscape. The orbital mechanics of this partnership follow mathematical laws so precise that astronomers can predict eclipses thousands of years in advance. The predictability extends to every aspect of the Earth-Moon system, from tidal patterns to the Moon's position against background stars. This reliability has made the Moon humanity's most trusted celestial companion, a cosmic clock that never needs winding and never loses time. The gravitational forces between Earth and the Moon create a feedback system that regulates both worlds. As the Moon raises tides on Earth, Earth's gravity holds the Moon in its orbital path. As the Moon's gravity slows Earth's rotation, the rotational energy gets transferred to the Moon's orbital motion. This energy exchange happens continuously but gradually, creating changes perceptible over human, so slow they're barely perceptible over lifetimes, yet significant over geological time spans. The Moon's surface contains impact glass that formed during some of the most violent events in solar system history. Yet these glass formations now create some of the most delicate and beautiful features on the lunar landscape. When large asteroids struck the Moon with incredible force, they melted vast quantities of rock that splashed outward like drops from a cosmic pond. This molten material cooled and solidified in space, creating streams and sheets of natural glass that flowed across the lunar surface. These impact glasses preserve the exact moment of their creation with remarkable fidelity. The chemical composition, the cooling patterns, and even tiny bubbles trapped within them tell stories about the asteroids that created them and the conditions that existed billions of years ago. Each glass formation is a snapshot of violence transformed into beauty, chaos crystallized into permanent art that will last longer than any human creation. The largest impact glass formations extend for hundreds of kilometers from their source craters, creating rays of glassy material that shine brilliantly when illuminated by the sun. These rays appear as bright streaks radiating from certain craters, visible even from Earth during a full moon. The glass reflects sunlight more efficiently than the surrounding rock, creating patterns that look almost like cosmic artwork painted across the lunar surface. Some impact glasses contain materials that aren't native to the Moon, fragments of the asteroids that created them. These alien inclusions provide rare samples of objects from the outer solar system, delivered to the Moon's surface by high-speed impacts. Scientists studying these glass formations can learn about the composition of asteroids and comets that formed in distant regions of space billions of years ago. The Moon's polar regions experience lighting conditions unlike anywhere else in the solar system, with some areas bathed in almost constant sunlight while others remain in perpetual darkness. The peaks of certain polar mountains catch sunlight for most of the lunar day and night cycle, making them some of the brightest places on the Moon's surface. These peaks of eternal light would provide ideal locations for solar power systems, receiving steady illumination while most of the lunar surface alternates between day and night. Meanwhile, the floors of deep polar craters exist in permanent shadow, creating regions colder than the surface of Pluto. These areas of eternal darkness have remained unchanged for billions of years, preserving collected there over geological time spans. The contrast between the sun, whatever materials have lit peaks, and shadowed valleys creates one of the most extreme environments in the solar system. with temperature differences of hundreds of degrees occurring within just a few kilometers. The boundary between light and shadow in polar regions remains remarkably stable over long periods, creating sharp dividing lines between the eternally illuminated and perpetually dark areas. These boundaries shift slightly with the moon's orbital motions and the subtle wobble of its axis, but they remain in approximately the same locations for thousands of years. Ancient ice deposits and other materials can accumulate right up to these boundaries, creating stark contrasts between preserved materials and areas where solar heating prevents any accumulation. The lighting geometry of polar regions also creates unique visual effects where sunlight skims horizontally across crater rims and mountain peaks. This low-angle illumination reveals surface textures and topographic details that would be invisible under the high-angle sunlight that characterizes most of the lunar surface. Shadows stretch for enormous distances, and small rocks cast shadows hundreds of times their actual size, creating a landscape of dramatic contrasts and unexpected beauty. The moon's regolith contains a complete record of meteorite impacts spanning billions of years, with each layer of dust and debris telling part of the story of our solar system's evolution. The oldest materials at the bottom of deep regolith layers preserve conditions from when the solar system was young and chaotic, while newer layers near the surface record more recent impacts and the gradual changes in the types of objects striking the moon. This layered structure creates a geological timeline that extends much farther back than any record preserved on Earth. While Earth's active geology constantly recycles surface materials, the moon's regolith accumulates and preserves everything that falls on it. Cosmic dust from interstellar space, particles from solar flares, fragments from asteroid collisions, and material from comet tails all contribute to this growing archive of cosmic history. The regolith layers also preserve evidence of changes in the sun's activity over geological timespans. During periods when the sun was more active, higher energy particles became embedded more deeply in lunar soil grains. During quieter periods, the particle energy decreased, creating subtle but measurable differences in the regolith layers. These variations provide a long-term record of stellar behavior that helps scientists understand how stars like the sun evolve over billions of years. Scientists can extract individual particles from different regolith layers and analyze them to understand the conditions that existed when they were deposited. Each grain carries information about the cosmic environment of its time, creating a library of solar system history that spans nearly the entire age of the planets. This information helps researchers understand not just lunar history, but the evolution of the entire solar system. The moon's synchronous rotation creates unique day and night cycles that last for 2 weeks each, producing the most gradual transitions between light and darkness found anywhere in the solar system. During the long lunar day, the sun moves so slowly across the sky that its motion is barely perceptible, creating lighting conditions that change almost imperceptibly from hour to hour. Shadows shift position with dreamlike slowness, and the quality of light evolves gradually over days rather than hours. This extended day-night cycle allows for thermal conditions that would be impossible on a faster rotating world. Rocks have time to heat all the way through during the long day, storing thermal energy that radiates away slowly during the equally long night. The gradual temperature changes create thermal expansion and contraction cycles that operate on completely different timescales from anything experienced on Earth. The 2-week day also means that any location on the moon experiences nearly constant lighting conditions for extended periods. A lunar base positioned on the day side would enjoy steady sunlight for 2 weeks, providing consistent conditions for solar power generation and outdoor activities. The extended daylight would eliminate the daily cycles of heating and cooling that complicate operations on Earth, replacing them with gradual, predictable changes that occur over much longer periods. During the transition from day to night, the Terminator moves across the lunar surface at walking speed, creating a moving boundary between vastly different thermal and lighting conditions. Standing near the Terminator would provide the unique experience of watching night slowly arrive, not as the sudden darkness of an Earth sunset, but as a gradual transition that takes hours to complete and transforms the landscape in slow motion. The moon's interior structure reveals a complex history of heating, cooling, and differentiation that played out over billions of years in the most patient geological processes imaginable. When the moon first formed from the debris of the giant impact, it was completely molten, a ball of liquid rock heated by the energy of accretion and radioactive decay. This magma ocean slowly cooled and solidified, with different minerals crystallizing at different depths as temperatures gradually decreased. The cooling process took millions of years, during which lighter minerals floated to the surface while denser materials sank toward the center. This differentiation created the layered structure we see today, with the light-colored anorthosite highlands representing the minerals that floated to the top of the magma ocean. The process was so gradual and thorough that it created distinct layers with different compositions, densities, and properties. As the moon continued to cool, its interior contracted slightly, causing the crust to wrinkle and crack in places. These ancient fractures created zones of weakness where later volcanic activity could reach the surface, forming the dark Maria we see today. The volcanic activity itself was driven by the slow release of heat from the moon's interior, a process that continued for over 1 billion years before the moon finally became volcanically quiet. Today, the moon's interior continues to cool at a rate so slow it's almost imperceptible. The core remains partially molten, still warm from the moon's formation 4.5 billion years ago. This residual heat drives the gentle moonquakes detected by seismic instruments and maintains the weak magnetic field that spacecraft can still measure. The cooling process will continue for billions more years, gradually reducing the moon to a completely solid, cold body. The moon's orbit creates a gravitational rhythm that influences Earth in ways both obvious and subtle, from the dramatic rise and fall of ocean tides to barely perceptible changes in the length of days. This gravitational pulse has remained steady for billions of years, providing a reliable celestial metronome that has helped regulate Earth's climate and rotation. The consistency of this influence has been crucial for maintaining the stable conditions necessary for life to evolve and flourish. The tidal forces generated by the moon's orbital motion don't just affect Earth's oceans, but also cause subtle flexing of the solid Earth itself. The planet's crust rises and falls by several centimeters twice each day in response to lunar gravity, a phenomenon called Earth tides that's completely invisible to human senses, but measurable by sensitive instruments. These solid Earth tides affect everything from underground water flows to the precise operation of particle accelerators. The moon's gravitational influence extends to Earth's atmosphere, creating atmospheric tides that cause subtle pressure variations following the lunar cycle. These atmospheric tides are much smaller than ocean tides, but they create measurable effects that meteorologists can detect in weather data. The gravitational pull even affects the height of the atmosphere itself, causing it to bulge slightly toward the moon in the same way that oceans create tidal bulges. The orbital rhythm also influences the Earth's magnetic field in subtle ways, as the moon's passage affects the flow of charged particles in the magnetosphere. During certain phases of the lunar orbit, when the moon passes through Earth's magnetic tail, complex interactions occur between the lunar surface and Earth's magnetic environment. These interactions create beautiful but invisible exchanges of energy and particles that demonstrate the interconnected nature of the Earth-Moon system. The lunar landscape preserves evidence of the early solar system's most violent period, when massive objects regularly collided with planets and moons in a cosmic bombardment that reshaped entire worlds. The moon's surface serves as a museum of this ancient chaos, with every crater telling the story of an impact that happened billions of years ago. Unlike Earth, where erosion and geological activity have erased most traces of early impacts, the moon maintains a perfect record of this formative period. The largest impact basins on the moon required asteroids the size of small planets to create them. The South Pole Aitken Basin, stretching across nearly a quarter of the lunar surface, was excavated by an impact so massive it nearly broke the moon apart. The energy released by this collision was equivalent to millions of nuclear weapons detonating simultaneously. Yet the moon survived and preserved the scar for billions of years. These ancient impacts did more than create craters. They fundamentally altered the moon's structure and composition. The largest impacts excavated material from deep within the lunar interior, bringing samples of the moon's mantle to the surface where they remain today. Some impacts were so powerful they created shock waves that traveled completely through the moon, affecting the far side even when the impact occurred on the near side. The bombardment period gradually ended as the solar system settled into its current configuration, with most large debris cleared away by planetary gravity. The moon's crater record shows this transition clearly, with older surfaces heavily cratered and younger surfaces showing fewer impacts. This gradual calming of the solar system allowed planets to develop stable conditions suitable for complex chemistry and eventually life. The moon's exosphere contains atoms that have been knocked free from the surface by solar wind and micrometeorite impacts, creating the thinnest atmosphere imaginable. This gossamer envelope changes constantly as atoms are added by impacts and lost to space, maintaining a delicate balance between supply and escape. The atmospheric density is so low that atoms rarely collide with each other, making the exosphere behave more like a collection of individual particles than a traditional atmosphere. Different parts of the lunar surface contribute different elements to the exosphere depending on their composition and exposure to solar radiation. Areas rich in sodium release sodium atoms that glow with characteristic yellow light when excited by solar energy. Regions containing potassium contribute potassium atoms that create their own spectral signatures. The result is an atmosphere with a composition that varies by location and changes with solar activity. The exosphere becomes slightly denser during periods of high solar activity when more atoms are knocked free from the surface, and it thins during solar minimum when fewer particles are available to replenish it. Seasonal variations also occur as the moon's orbit carries it through different regions of space with varying particle densities. During certain parts of its orbit, the moon passes through Earth's magnetosphere, where conditions are different from the solar wind environment. This tenuous atmosphere occasionally produces phenomena that would be impossible in a denser atmosphere. Atoms can travel thousands of kilometers before falling back to the surface or escaping to space, creating ballistic trajectories that arc high above the lunar surface. Some atoms escape the moon's gravity entirely and become part of the interplanetary medium, while others eventually return to the surface far from where they originated. The moon's role as Earth's stabilizing partner extends far beyond preventing chaotic wobbling to include maintaining the delicate balance of forces that keeps our planet's climate system functioning predictably. Without the moon's gravitational influence, Earth's obliquity would vary wildly over time, causing dramatic shifts between ice ages and greenhouse periods that would make long-term climate stability impossible. The moon acts as a cosmic gyroscope, holding Earth steady against the gravitational perturbations of other planets. This stabilization has been crucial for the evolution of complex life on Earth. The consistent seasonal patterns created by stable obliquity have allowed ecosystems to develop reliable cycles of growth, reproduction, and dormancy. Ocean currents follow predictable patterns because of the moon's tidal influence, distributing heat around the globe and maintaining the temperature gradients that drive weather systems. The moon's influence on Earth's rotation rate has also been essential for creating habitable conditions. The gradual slowing of Earth's rotation has increased the length of days from the original 6-hour periods to our current 24-hour cycle. This slower rotation allows for more moderate temperature differences between day and night, preventing the extreme heating and cooling that would occur with rapid rotation. The tidal mixing caused by the moon's gravity helps oxygenate Earth's oceans and distribute nutrients essential for marine life. Without this gentle stirring action, the oceans might become stratified and stagnant, with deep waters becoming depleted of oxygen and surface waters becoming nutrient poor. The moon's tidal influence maintains the circulation patterns that keep Earth's oceans healthy and productive. The moon serves as a natural laboratory for studying processes that no longer occur on Earth, preserving conditions and materials from the early solar system in a pristine state impossible to find on our geologically active planet. The lunar surface maintains samples of the solar wind, cosmic radiation, and interplanetary dust exactly as they were when deposited billions of years ago. This preservation allows scientists to study the history and evolution of the sun, the solar system, and the galaxy itself. The lack of atmospheric weathering on the moon means that impact materials remain chemically unchanged from the moment they were created. Glasses formed by ancient impacts retain their original composition, providing direct samples of the asteroids and comets that struck the lunar surface. These materials offer insights into the composition and evolution of small bodies throughout the solar system's history. The moon's seismic activity provides information about planetary interiors that complements what we learn from Earth's more complex geology. Moonquakes follow different patterns from earthquakes because of the moon's different internal structure and thermal state. The way seismic waves propagate through the moon reveals details about its internal layering, density variations, and the physical properties of rock at different depths. The electromagnetic environment around the moon offers unique opportunities to study space physics processes, without the complications introduced by Earth's strong magnetic field and thick atmosphere. Solar-wind interactions with the lunar surface create phenomena that help scientists understand how similar processes might work on other airless bodies throughout the solar system. The moon serves as an accessible natural laboratory for studying fundamental processes that operate throughout the cosmos. The moon's relationship with time itself reveals one of the most poetic aspects of our celestial companion, as it serves as both timekeeper and time capsule simultaneously. While we use the moon's phases to mark the passage of months and seasons, the lunar surface preserves moments from billions of years ago in perfect detail. Every grain of regolith, every crater rim, every glass bead formed by impact carries within it the exact conditions that existed when it was created, making the moon a living archive of cosmic history. This temporal paradox means that standing on the lunar surface would place you simultaneously in the present moment and in the distant past. The rock beneath your feet might have crystallized when the solar system was young and chaotic, while the dust around you could contain particles that arrived just yesterday from distant corners of the galaxy. The moon doesn't experience time the way Earth does, with its constant recycling and renewal, but instead accumulates time like layers in an ancient book. The moon's influence on Earth's biological rhythms connects our daily lives to cosmic cycles in ways that science is still discovering. Many organisms on Earth follow circadian rhythms that roughly match the 24-hour day, but some also respond to circulunar rhythms that correspond to the moon's 29.5-day cycle. These biological clocks appear to be hardwired into life itself, suggesting that the moon's influence extends far beyond the physical effects of gravity and tides. Certain marine organisms synchronize their reproductive cycles not just to tidal cycles, but to specific combinations of lunar phase and tidal conditions that occur only a few times each year. Some corals spawn only during particular full moons, releasing millions of eggs and sperm into the water in precisely timed events that maximize the chances of successful reproduction. These biological calendars have been running for millions of years, creating an intimate connection between earthly life and lunar cycles. Research suggests that human sleep patterns may also be subtly influenced by lunar cycles, though the effects are much weaker than the obvious responses seen in marine life. Some studies indicate that people tend to sleep slightly less during full moon periods, possibly due to evolutionary adaptations from times when bright moonlight affected nighttime activities. While the evidence remains debated, it hints at connections between human physiology and cosmic rhythms that extend back to our earliest ancestors. The moon's surface contains natural laboratories where the most extreme physics experiments in the solar system have been running for billions of years. The combination of vacuum conditions, extreme temperature variations, and constant bombardment by cosmic radiation creates environments that cannot be replicated on Earth. Materials undergo transformations under these conditions that provide insights into fundamental physical and chemical processes. Space weathering on the moon occurs through mechanisms that don't exist on Earth, gradually altering the optical and chemical properties of surface materials over geological time spans. Solar wind particles implant themselves into crystal structures. Cosmic rays create microscopic damage tracks, and micrometeorite impacts vaporize tiny amounts of material that recondense in altered forms. These processes work so slowly that they're invisible to human observation, yet over millions of years, they can completely transform the appearance and composition of lunarolith Ax rocks. The moon's reg as a vast particle accelerator detector, recording the passage of high-energy cosmic rays over billions of years. These particles, accelerated by distant stellar explosions and galactic magnetic fields, leave traces in lunar minerals that scientists can study to understand the radiation environment of our cosmic neighborhood throughout geological history. The moon serves as a passive instrument that has been collecting data about cosmic rays longer than any human detector could possibly operate. The thermal cycling experienced by lunar materials creates unique crystalline structures that don't form under Earth's more moderate conditions. The extreme temperature swings between lunar day and night, repeated countless times over billions of years, forge materials with properties that might prove useful for future technologies. The moon's surface has essentially been conducting materials science experiments at cosmic scales, creating samples that represent billions of years of research and development. The moon's gravitational field contains subtle irregularities that create invisible sculptures in space, shaping the paths of particles and spacecraft in ways that reveal the hidden architecture of the lunar interior. These gravitational anomalies, formed by dense material concentrations beneath the surface, act like invisible hills and valleys that influence everything from dust particle trajectories to satellite orbits. The gravitational landscape around the moon is as complex and beautiful as its physical topography. Spacecraft orbiting the moon must navigate these gravitational variations like ships sailing through invisible currents and eddies. The mass concentrations associated with large impact basins create regions where orbital mechanics work differently, requiring constant adjustments to maintain stable paths. These gravitational features demonstrate that space around the moon is not empty and uniform, but filled with invisible structures that shape motion and behavior. The moon's weak magnetic field creates pockets and streams of magnetic force that interact with the solar wind in complex ways. While much weaker than Earth's magnetic field, these lunar magnetic anomalies create their own miniature magnetospheres that deflect charged particles and create localized space weather phenomena. Some regions of the lunar surface are partially shielded from solar wind by these magnetic umbrellas, while others remain completely exposed. These magnetic variations also affect the behavior of charged dust particles on the lunar surface, creating regions where electrostatic levitation is more or less likely to occur. The interaction between magnetic fields, electric charges, and dust particles creates a dynamic environment that changes with solar activity and the moon's position relative to Earth's magnetic field. The result is a complex electromagnetic ecosystem that operates according to principles of space physics. The moon's ancient volcanic activity created some of the most perfect natural glass formations in the solar system, preserved in pristine condition by the airless environment. When lunar volcanoes erupted billions of years ago, they produced lava flows that cooled and solidified under conditions impossible to replicate on Earth. The absence of atmosphere meant that volcanic gases escaped freely, creating rock textures and mineral formations that tell unique stories about planetary volcanism. The lunar Maria represent the moon's most peaceful period, when internal heat drove gentle effusions of lava that filled the largest impact basins with dark, smooth plains. These volcanic flows occurred over millions of years, layer upon layer of molten rock spreading across the lunar surface like slow cosmic honey. The lava moved so gradually that it flowed around obstacles and filled depressions with extraordinary precision, creating the smooth surfaces we see today. Some lunar lava flows created natural tunnels called lava tubes when the surface of a flow cooled and hardened while molten rock continued to flow beneath. These tubes, some large enough to contain entire cities, remain perfectly preserved beneath the lunar surface. They offer natural protection from radiation and meteorite impacts, creating ready-made spaces that future lunar explorers might use as shelters or bases. The composition of lunar volcanic rocks reveals details about the moon's interior chemistry and thermal evolution that complement complex volcanic what we learn from Earth's more systems. Lunar basalts formed under different pressure and temperature conditions than their earthly counterparts, creating mineral assemblages that provide insights into planetary differentiation and magma ocean crystallization processes that operated during the early history of rocky worlds. The moon's position in space creates unique astronomical phenomena that occur nowhere else in the solar system, turning our satellite into a natural observatory with perspectives impossible to achieve from Earth. The moon's synchronous rotation means that telescopes placed on the far side would have unobstructed views of deep space, never interrupted by Earth's brightness or radio interference. This permanent darkness makes the far side one of the most valuable pieces of real estate in the solar system for astronomical research. The moon's lack of atmosphere eliminates the twinkling and blurring effects that limit ground-based astronomy on Earth, allowing theoretical telescopes on the lunar surface to achieve perfect resolution, limited only by the fundamental physics of light and optics. Stars would appear as perfect points of light, galaxies would show crisp detail, and faint objects currently invisible from Earth would become accessible to observation. The low-gravity environment would allow construction of enormous telescopes that would collapse under their own weight on Earth. Mirrors hundreds of meters across could be built and supported using structures that would be impossible to create in Earth's stronger gravitational field. The moon's stable geology means that these instruments could maintain perfect alignment for centuries without the constant adjustments required by Earth-based telescopes. The moon's orbital motion around Earth provides a natural baseline for parallax measurements, allowing astronomers to determine distances to nearby stars with extraordinary precision. As the moon moves through its orbit, telescopes on its surface would have access to observation angles separated by the full diameter of the lunar orbit, creating opportunities for three-dimensional mapping of stellar neighborhoods that extend far beyond our current capabilities. The lunar regolith contains a chemical record of the sun's composition and activity that extends back to the earliest days of the solar system that have been accumulated, preserved in particulating grain by grain for billions of years. Solar wind particles become implanted in the crystal structures of lunar minerals, creating microscopic time capsules that preserve samples of the solar atmosphere from different epochs in stellar evolution. By analyzing regolith samples from different depths and locations, scientists can reconstruct the history of solar activity over geological timespans. Periods of high solar activity left different chemical signatures than quiet periods, creating a layered record that reveals how the sun's energy output has changed over billions of years. This information provides crucial data for understanding stellar evolution and predicting future solar behavior. The regolith also contains particles from beyond our solar system, interstellar grains that originated in distant stars and traveled across the galaxy before settling gently on the lunar surface. These microscopic visitors carry information about stellar nucleosynthesis, galactic chemical evolution, and the composition of the interstellar medium. Each grain represents a sample from a distant world, delivered free of charge by the natural processes of cosmic circulation. The preservation of these particles in lunar regolith is so perfect that they retain their original isotopic compositions, allowing scientists to identify their stellar sources and understand the nuclear processes that created them. Some grains are older than the solar system itself, predating the formation of Earth and the Moon by millions of years. They provide direct samples of the galactic environment that existed before our solar system formed. The Moon's thermal environment creates conditions for natural processes that operate on timescales unimaginable from human perspectives, yet produce effects that accumulate into significant changes over geological time. The extreme temperature cycling between lunar day and night causes rocks to expand and contract repeatedly, creating microscopic fractures that gradually weaken the material and contribute to the slow breakdown of solid rock into regolith. This thermal weathering operates so slowly that individual cycles produce changes too small to measure. Yet over millions of years, the cumulative effect reshapes entire landscapes. Boulders slowly crack and crumble, crater walls gradually slump and round off, and sharp edges become softened by the patient work of thermal stress. The process transforms the Moon's surface at a pace that makes geological time seem rushed by comparison. The temperature gradients beneath the lunar surface create convection patterns in areas where subsurface ice might exist, potentially driving the slow migration of water molecules through the regolith over geological timespans. These movements operate according to principles of thermodynamics, but at speeds so slow that the migration of water molecules becomes a geological process rather than a fluid dynamic one. The Moon's surface acts as a massive solar collector during the long lunar day, absorbing and storing thermal energy that radiates away slowly during the equally long night. This energy storage and release cycle creates temperature patterns that influence everything from the sublimation of ice deposits to the electrical charging of dust particles. The thermal mass of the lunar surface creates a heat reservoir that moderates the most extreme temperature swings and provides thermal inertia that affects surface processes in subtle but important ways. The Moon's relationship with cosmic dust reveals another layer of its role as Earth's protector and cosmic companion. Throughout its orbital journey, the Moon encounters streams of particles from asteroid collisions, comet tails, and interplanetary debris. Its gravitational field captures some of this material while deflecting other particles away from Earth, acting as both a cosmic dustpan and a gravitational shield. The captured particles become part of the lunar regolith, contributing to the slow but steady growth of the lunar soil layer. Each particle that lands on the Moon represents a tiny piece of the solar system's ongoing evolution, a microscopic sample of materials that originated in the asteroid belt, the outer planets, or even more distant regions. The Moon collects this cosmic debris without bias, creating an archive of solar system materials that spans its entire history. Some of the dust particles that approach the Earth-Moon system get perturbed into different orbits by lunar gravity, either falling into Earth's atmosphere where they burn up as meteors or getting scattered into different parts of the solar system. This gravitational influence helps regulate the amount of cosmic debris that reaches Earth's vicinity, providing a subtle but important protective effect for our planet. The moon's dust-collecting activities also create faint but measurable changes in its mass over geological time. While individual particles are microscopic, the cumulative effect of billions of years of dust accumulation adds measurable mass to the lunar system. This mass increase is infinitesimal compared to the moon's total mass, but it represents a real contribution from the ongoing processes that shape our cosmic neighborhood. The moon's seismic activity provides a window into planetary processes that operate deep within rocky worlds, offering insights into the behavior of materials under conditions that cannot be replicated in earthly laboratories. Moonquakes occur at depths and pressures that reveal how rock behaves in the interiors of planetary bodies, providing data that helps scientists understand the internal dynamics of Earth and other rocky planets throughout the universe. The deep moonquakes that originate hundreds of kilometers below the surface occur in response to tidal stresses created by Earth's gravitational pull. These seismic events happen with such regularity that they create a kind of cosmic heartbeat, a rhythmic pulsing that reflects the ongoing gravitational interaction between Earth and the Moon. The pattern of these deep quakes follows the lunar orbital cycle with such precision that seismologists can predict when they will occur. Shallow moonquakes, which happen closer to the surface, appear to be related to the gradual cooling and contraction of the lunar interior. As the moon continues to lose heat accumulated during its formation billions of years ago, its interior slowly shrinks, creating stresses that occasionally release as seismic events. These quakes provide evidence that the moon remains geologically active, even though its volcanism ended long ago. The way seismic waves propagate through the moon reveals details about its internal structure that would be impossible to determine from surface observations alone. The moon's interior acts like a natural seismic laboratory with its dry, rigid structure allowing waves to travel farther and remain coherent longer than they would in Earth's more complex internal environment. This clarity-ismic signals provides unique, obscurely detailed information about planetary interiors. And so our gentle journey through the moon's most soothing mysteries draws to a close. We've drifted together across billions of years and countless kilometers, discovering that our celestial companion is far more than just a bright disk in the night sky. From the soft regolith that sparkles like cosmic flour to the ancient glass beads that preserve moments from the dawn of time, each lunar secret we've explored tonight carries within it a profound sense of peace and permanence. The moon continues its patient dance around Earth, moving away at the pace of a growing fingernail, creating tides with the gentleness of a cosmic breath, and keeping the same faithful face turned toward us as it has for billions of years. In its craters, we find stories of violence transformed into beauty. In its phases, we discover the rhythm of celestial breathing, and in its gravity, we feel the tender embrace that has kept our planet stable throughout the entire history of life. As you settle deeper into rest tonight, perhaps you'll carry with you the knowledge that, high above, our lunar companion continues its eternal vigil. The same moon that has watched over countless generations of dreamers now watches over you, casting its silver light through your window and whispering its ancient lullabies across the vast darkness of space. Sweet dreams, and may the moon's gentle mysteries carry you peacefully through the night.